Hello. So this will be a discussion on moment of inertia and how to do some simple uh, rigid body equilibrium problems. So let's first do some simple calculations of moment of inertia. So moment of inertia turns out to be the equivalent of mass somehow when you're talking about rigid extended objects. So let's say we want to find out what moment of inertia of an object is. Then moment of inertia, usually denoted by the symbol I, is by definition a sum, and the sum is over every mass point. Let's call it m sub I, and the location of that mass point r sub I with respect to the axis of rotation of the rigid body itself, and r sub I is squared, and then you sum over all i's. So this is how it is defined. So let's say we have some irregular shaped object that is turning about some axis here. And let's say the object is like this. And this object is turning about an axis that I have shown. Then I can pull out, for example, some mass points here. For example, this can be a mass point M1. And this M1, let's say, is at a distance. This is the shortest distance you can construct, R1, from the axis. Likewise, I can have another mass point, which can be M2, and the distance here would be R2. And likewise, you can have an M3, and the distance here would be R3, and so on and so forth. So that's how one constructs the moment of inertia of an object. So this, of course, is a grueling calculation when you're trying to do a complicated object. Let's talk about, for example, an asteroid. An asteroid typically can be quite an irregular shaped object. There are small pieces of rock that you find in a band between Mars and Jupiter. And they often come and visit us nearby. So most of us have seen pictures of them. I'm sure you have seen some. So if you want to calculate the moment of inertia of an asteroid, which is an ideal example of an irregular rigid body, which is also rotating about perhaps some axis, then you can think about the example I just gave. Let's take a more regular object and show you how to calculate moment of inertia of a simple object. For example, you have 4 masses, like so. And these masses are connected by some light rod. And let's say the masses are much heavier than the light rod. In which case we can regard these light rod masses to be approximately equal to 0. And these masses, let's call them big M. So they're the same in magnitude. And let's say I draw an axis here. Let's say the axis is about the center. Let's say, it's right about like this. It can be vertical or horizontal. The calculation doesn't really change. And let's say this distribution of 4 masses is rotating about this axis. I don't particularly care about the rotation. I'm just interested in calculating the moment of inertia of the distribution of masses about the axis. Let's call it AB. And let's say the sides here each are of length A. So in that case, I can simply say that the moment of inertia I would be m times a over 2, because that's the perpendicular distance. A over 2 being this distance here, and this distance here. These are all a over 2. And same here. So I have m times a over 2 square, because that's mr square. And then I have 4 mass points. So it'll wind up being simply ma square. So you can see it's a very straightforward calculation. Now the axis does matter though. So for example, if I take the same object and that I just took, let's say I took these 4 masses. And now instead of having the axis I had, I now run an axis like so. So now you see things will change a little bit, because 2 of the masses are sitting right on the axis itself. Let's call this axis CD. So these 2 masses are sitting right on the axis itself, which means that the distance of these masses from the axis is 0, which means that we only are interested in the perpendicular distance involved here. This is not the best possible drawing, I'm sorry. Doesn't quite look like a perpendicular, but that's, let me try and fix that if you'll let me. Let's say I put something here and this is my mass, and let's say I put something here and this is my mass, and that these are perpendicular distances, so 90 degrees, and these of course are m. So let's just be a little savvy here. So this one is a and this one is a, which means by Pythagoras theorem, this whole length between is square root of 2a. The reason is that Pythagoras theorem tells us that a square plus a square is equal to 2a square, which is the diagonal. And then the length of the diagonal, this is the diagonal square, is hence, this is the length of the diagonal. Right? So it's easy then to see that this particular distance here is going to be square root of 2 times a divided by 2, which means it's going to be a divided by square root of 2. And same will be the case here. This will also be a divided by square root of 2. Therefore, the moment of inertia about axis CD, let's call this axis AB. And let's call this axis CD. And what we'll see now is something quite interesting, as you'll just wait and see what happens. So we have 2 masses. Each of them would be m, and the distance the perpendicular distance they have is a over root 2. So we square this. That gives me the moment of inertia about each of these masses. And then there are 2 of these masses. So now what happens is I'm left with m times a square over 2 times 2. And lo and behold, I actually end up with the exact same value of the moment of inertia that I had in the beginning. So in the first case, about AB, that is. And the reason why this happens, if you will, is because while axis CD indeed is placed farther than the 2 m's here, these 2 masses, the other 2 masses are actually sitting on top of it, and that kind of compensates for the increase in moment of inertia, because 2 of the masses are sitting far from where they used to be in the case of axis AB, okay? So these are 2 simple examples of how to calculate moment of inertia. We'll also obviously be dealing with moment of inertia of items such as spheres, but we will not indulge in calculation of the moment of inertia of a sphere about an axis. Sorry. And here the moment of inertia, I about the axis, for a solid sphere is 2/5 mr square, where m is the mass of the sphere and r is the radius. And 2/3 mr square if it's a hollow sphere. So I hollow and I solid. Similarly, we have the disk, and the disk is 1/2 mr square, and so on and so forth. So let's move on to a quick discussion of rigid body equilibrium in the next page. So there are two standard problems that I want to quickly discuss. So rigid body equilibrium problems. So let's say we take an example, a very standard example, and this is an example of a shelf, let's say, or perhaps even a rod. So this is viewed sideways. That is embedded somehow, okay? So let's extend this a little bit. And then what we have is that this is our wall. The way it is done is that this shelf that you have, this shelf here, is embedded into the wall, so it has a certain mass and therefore an mg and therefore a w, a weight w. Let's say the length of this is L. The exact value of L is not very important right now. And let's say we find it meaningful to have some kind of a string. Let's give it some, well, maybe call this point A, call this point B, and call this point C. Let's join from B to C with a string, and the string will be holding this shelf in place such that it doesn't fall, which means the string will exert a tension in the direction shown. Let's call it T, and let's call this angle here theta. So we have drawn up W and tension T. Let's also try to imagine what might be happening in the neighborhood of point A, where the shelf goes into the wall. You know very well that if you stick a shelf in the wall, there'll be some kind of force acting on the wall, because the wall can get damaged and it can break and so on, right? So it's not very difficult for us to imagine that. Let me move the location of it a little bit. I'll put it here. Not difficult for us to imagine that there are some forces at play here. And we can generically think about these forces as a horizontal force, Hx, and a vertical force here, Hy. So given what we have here, let's try to construct the equation for the forces. Let's construct the equation for forces along x direction. And along x direction, well, we should first split up the tension force T. So let's say we take a vertical component, that will be T sine of theta here. And then there'll be a horizontal component. And let's call this T cosine of theta here. So along x direction, we have Hx moving to the right, so Hx, and leftward force will be T cosine of theta. And since the system is in equilibrium, the right side of the equation for force is 0. Likewise, we can take for y. And for y, we have two vertical forces. We have Hy, then we have T sine theta, so plus T sine theta, minus W is equal to 0. And of course, along with equation for forces, we also need to make sure that this rod doesn't have a tendency to turn, which means that we want to set up the torque equation. And the torque equation, we will take torque about point A. Now here is an important issue that I should address. Let's give this point a color. Oops. This is the color. This is the point A. If you think about it, the force Hx will pass through this point, and hence it will not have a torque. The force Hy will also pass through this point, and hence not have a torque. Further, since forces can be translated, the force T cosine theta will also pass through this point, and hence not have a torque. So by choosing point A as the point to take torque about, you have killed off the torque contributions of three forces. And this greatly simplifies the torque equation. So how you construct your torque equation is actually quite important. So what we'll do is we'll take torques then only for these two forces, because these are the only two surviving forces. I'm going to put in some green color just to mark it up. So one of them would be W, and the other would be this force here, T sine theta, okay? So for W, we'll get W times L upon 2, and the torque would generally be in this direction, which would mean clockwise. So let's say clockwise is minus. And then you have T sine of theta, and that's at a distance L from A. And this would generate a torque, if you will, in this direction, which would be counterclockwise. So let's call it plus. And then the net torque should be 0 for equilibrium. So this problem now is actually quite simple, because we have managed to take advantage of the number of forces that are passing through point A. So if you look at the torque equation, you can immediately see that we don't need to know L, because we can actually cancel out L. So therefore, we can write T sine theta is equal to W. So if I know W, then T is going to be W divided by sine theta. So that means I figured out what T is. So by knowing, suppose W is known, I put a circle around it. And of course, I have to know theta, so I put a circle around it. If I know these two quantities, then I can certainly find the tension T. Now, once I know the tension T, that means from X equation, I know Hx. And once I find tension T from Y equation, I actually can also find Hy. So as you can see, that just by knowing W and theta, we can get to know the tension T, Hx, and Hy. What I do not need to know in this particular case, in the way I've constructed the problem, is the length of this shelf, which is quite interesting that the length of the shelf doesn't really play a huge role here. Let me do another simple problem, and that's that of the leaning ladder. The leaning ladder is a problem like this, where you have, let's say, a rough surface, and then you have a wall. And you place a ladder here, okay? So if you place a ladder here, at the simplest case, nobody's standing on the ladder right now. You can put somebody on the ladder. It just makes the calculation a little bit more laborious. But and let us say I know the angle theta, or somehow equivalent of angle theta, okay? And let's say the length of this ladder is L. Clearly, let's mark up some points. Let's call this point A. Let's call this point B. Let's call this point C. If you look at A, the ladder will have a tendency to slip in the leftward direction, which means the friction would be opposing that shift, and hence would be in the rightward direction. So let's call F friction like this. I'm going to move this a little bit, if you don't mind, like so. Then I can write, there is some other vertical force that should come into play as a reaction force. It doesn't exactly matter how this force is looking like, in which direction and so on, but a vertical force assumption is a fine assumption, because any force can be split into a horizontal and a vertical component, which is what we are doing, so we are okay. Similarly, there should be some force at C. I don't know what that force is, but for simplicity, let's only consider a horizontal force. And let's call this a normal force N2. So I have everything I need, I think. So let me first set up a force equation. And the force equation here is quite straightforward. I have F friction, and then N2 moving in the other direction. So that would give me a 0. Likewise, as far as Y equation is concerned, I have N1 minus W is equal to 0. And as far as torque equation is concerned, I again must identify about which point it is going to be most beneficial for us to take torque. Clearly, if you look at point A, you see there are the force F friction passes through point A, and hence F friction will not give us a torque. Likewise, N1 passes through point A. It won't give us a torque. So we can already eliminate two of the contributing torques from the problem if we select point A as the point about which you take torque. So what I'll do is I'll take the torque of W. You see, W is at a distance from A. This particular distance here is going to be L cosine theta. So W is L over 2 cosine of theta from A. Okay, so, and this is going to generate a torque in that direction, which is clockwise, so let's call it minus. And likewise, I'll have a torque coming from N2. If I extrapolate N2, then I can immediately see that the perpendicular distance of N2 from A is actually nothing but L sine theta. So therefore, I should write N2 times L sine theta. And this is going to be a torque in the counterclockwise direction, so make it plus, and that should be equal to 0. So I've actually set up all the equations. From the torque equation, I can see that N2, just like before, N2 will turn out to be or let me just rewrite this. So N2 times sine theta is going to be W over 2 times cos theta. As you can see, I've eliminated L because L shows up in both the terms and L is not 0. So therefore, knowing if I know W, which is the weight of the ladder, and if I know theta, just like before, then I can find out what N2 is. And N2 is going to be W over 2 cos theta over sine theta. Okay. So knowing W, N2 can be found. X equation then means N2 would imply knowledge of the friction force. In fact, the two should be the same. And knowing from Y equation, knowing W would mean N1 is also known. So let me write it this way, that W alone means N1 is also known. So we have found N1, we have found F friction, and we have found N2, all the forces that need to be found by doing this torque problem. So at this point, I would close this. Thank you for your attention.